Something is happening to the visitor from another star. July 1st, 2025. Atlas Survey Telescope in Chile picks up an object moving fast. Too fast. The numbers come back. Eccentricity, 6.14. That means one thing. It came from outside. Third confirmed interstellar object ever detected. They name it 3I Atlas. By September, it glows green. Cyanide and dicarbon in the coma. Normal comet behavior. Then October 29th rolls around. Perihelion. 1.36 astronomical units from the Sun. Behind our star from Earth's view. Ground telescopes lose it. But solar observatories keep watching. Stereo A Soho goes 19, and what they see makes no sense. The comet turns blue. Bluer than the Sun itself. You hear about comets all the time. Dirty snowballs, ice and rock. They heat up near the Sun and glow. Red dust. Maybe some green from carbon molecules. Standard physics. 3I Atlas breaks that script. Between mid-September and late October, the brightness surges. Not gradually, exponentially. The team measures it. Brightness scales with distance to the power of -7.5. Most Oort cloud comets, maybe -2 or 3. This thing brightens at twice the normal rate. No established explanation exists for that behavior. Then the color data drops. LASCO coronagraph, CCOR-1 instrument. Color photometry confirms it. The comet appears distinctly bluer than sunlight. Chicheng Jiang from Lowell Observatory and Carl Battams from U.S. Naval Research Laboratory published the preprint October 28, 2025. Posted to AR-Xiv. They write it clear. The comet's blue appearance suggests gas emission contributes substantially to visible brightness near perihelion. But here's the problem. Dust reddens scattered light, always. The comet's surface temperature sits around 580 degrees Kelvin. The Sun's photosphere, 5,800. An object 10 times colder should look redder, not bluer. The blue color at perihelion becomes the 9th documented anomaly for this object. If you value documented astronomical history like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual using sources from the AR-Xiv preprint server, where Jiang and Battams published their rapid brightening analysis on October 28, 2025, and from the peer-reviewed paper by Rohan Rahatgaonkar and the VLT team published August 25, 2025, documenting nickel emission evolution from July through August. Now back to the information. The chemistry tells a stranger story. July 20th, 2025, Very Large Telescope in Chile, European Southern Observatory, X-shooter and UVES spectrographs lock onto 3I Atlas. Distance 3.88 astronomical units from the Sun, nearly 4 times Earth's distance. Way too cold for metal to vaporize. They detect nickel, atomic nickel vapor. 22 emission lines. Strongest ones at 3,414.8 angstroms and 3,524.5 angstroms. No. Comet releases nickel that far out. Temperature should be 70 degrees below the sublimation point, but there it sits in the spectrum, clear as glass. Here's where it gets weird. They look for iron. Iron and nickel always appear together. Same supernova origin, same meteoritic ratios, cosmic twins. The VLT team scans the full wavelength range. No iron. Not a single Phi line above detection limits. Nickel without iron. That doesn't happen in nature. Not in solar system comets, not in asteroids, not in interstellar dust. The decoupling contradicts everything we know about refractory metal release, industrial nickel refining. On Earth separates the two. Nickel-titanium alloys. Shape memory applications, that's the only place you see pure nickel emission without iron contamination. But this is a comet from another star system, not a factory. The emission rate climbs. July 20th, 4.6 grams per second. August 21st. Rate increases steadily as the comet approaches from 4.4 astronomical units down to 2.85. By the final VLT measurement, the nickel production hits 21.26 atoms per second with an uncertainty of 0.30. The team led by Rohan Rahatgaonkar publishes the findings August 25, 2025, posted on Airarchia. They propose a hypothesis. Organometallic compounds, nickel bound to carbon monoxide molecules, nickel tetracarbonyl. That substance sublimates at low temperatures, around 76 to 79 degrees Kelvin. Way below standard metal sublimation points, the compound breaks apart in sunlight, releases nickel atoms, leaves no iron because iron pentacarbonyl needs higher temperatures to sublime. Chemistry that works at a distance where solid metal should stay frozen. Then cyanide appears. August 14, 2025. Lowell Observatory reports tentative CN detection. VLT confirms it, August 21st. Production. Rate 17.6 grams per second plus or minus 2. The CN extends farther into the coma than nickel. Nickel concentrates in the inner 2,000 kilometers. Cyanide spreads wider. Different parent molecules, different thermal thresholds. HCN for cyanide. NiCO4 for nickel. The temperature gradient in the coma reveals layered chemistry, like reading a cross-section of the nucleus composition. August 6, 2025. James Webb Space Telescope points NIR spec at 3I Atlas, distance 3.32 astronomical units. Infrared spectroscopy, 0.6 to 5.3 micrometers. The results rewrite comet. Chemistry. Carbon dioxide dominates, not water. The CO2 to H2O ratio hits 7.6 plus or minus 0.3. Some measurements show 8 to 1, highest ever recorded in a comet. Most comets show water dominance, maybe 1 part CO2 for every 2 or 3 parts water. 3I Atlas flips it, 8 parts carbon dioxide for every 1 part water. Martin Cordner from NASA, Goddard and Catholic University of America leads the study. Published August 25, 2025. The finding sits 4.5 sigma above the trend line for long. Period and Jupiter family comets. Statistical outlier. Clear deviation. The spectrum shows more. Water vapor, carbon monoxide, carbonyl sulfide, water ice, dust, but carbon dioxide overwhelms everything. Production rate 129 kilograms per second. Water, 6.6 kilograms per second, 20 times more CO2 than water by mass. The James Clerk Maxwell Telescope measures hydrogen cyanide, September 7th, 1.5 times 10 to the 25th molecules per second. Week later, September 14th, it triples, 4.5 times 10 to the 25th molecules per second. 2 kilograms per second of cyanide pouring into space. The coma on September 15th stretches 180,000 kilometers, asymmetric, elongated in the anti-solar direction, dust tail 50 arcseconds wide, 100,000 kilometers of debris. The carbon isotope ratio gives clues. Carbon-12 versus carbon-13, roughly solar, similar to Earth. The material formed in an environment with familiar carbon chemistry, but the volatile ratios scream difference. That CO2 dominance means something. 2 possibilities. First, the nucleus formed beyond the carbon dioxide ice line in its home protoplanetary disk, way out where CO2 ice becomes more abundant than water ice. Second, extreme radiation. Processing. Cosmic rays, ultraviolet bombardment, millions or billions of years in interstellar space. Radiation strips away volatile ices. Water sublimates first, carbon monoxide next, carbon dioxide lingers. Surface layer gets enriched in the most radiation-resistant compound. Either scenario works. Both suggest a formation environment radically different from solar system comets. Sphere-X Observatory catches it mid-August. Carbon dioxide cloud extending 348,000 kilometers from the nucleus. Massive. The Punch satellite constellation images it, October 27th. Filter centered at 0.55 micrometers. Co-added stack. The object glows against the starfield. Then, Perihelion happens. October 21, 2025. Solar conjunction from Earth. 3I Atlas passes behind the Sun. Ground-based telescopes go blind. The comet sits 14 degrees above the horizon for observers in Manciano, Italy by early November, but during perihelion approach only space-based solar monitors can track it. Stereo A's Secchi Suite, Chai 1 and Kior 2 cameras, wide field imaging, Soho's Lasco C3 coronagraph, wavelength range 520 to 770 nanometers, GOES 19 weather satellite, CCOR-1 compact coronagraph, launched 2024, space weather monitoring, all routine observations, not special targeting. Just happens 3. IATLAS crosses their fields of view. The instruments catch the brightening. September through October. Distance drops from about 2 astronomical units to 1.36. Brightness explodes. Power law with exponent negative 7.5 plus or minus 1. Zhang and Battams calculate geocentric V magnitude around 9 at perihelion. Bright enough for small amateur telescopes, binoculars even, but hidden in solar glare. CCOR-1 resolves extended structure. Coma 4 arc-minutes in diameter, 300,000 kilometers across, matches the Sphere-X carbon dioxide plume scale from August. The whole atmosphere glows. Then the color shift registers. Earlier August observations, red, dust-dominated, reflected sunlight off mineral particles, standard comet appearance. Late October, near perihelion, blue, Lasco color photometry, CCOR-1 color photometry, both confirm, distinctly bluer than the sun. Gas emission, not dust reflection. The shift indicates carbon molecules, dicarbon, C2, possibly amino radicals, NH2, both fluoresce under ultraviolet radiation, both emit blue-green wavelengths. The ionized gas tail grows. Plasma, charged particles stripped by solar wind, always points away from the sun. Ion tail structure becomes more defined, more complex. Jets visible, multiple outgassing regions across the nucleus surface. Virtual, telescope project in Manciano, Italy. Gianluca Massi captures images November 6th after the comet re-emerges into morning sky. Then November 10th. 11:31 p.m. Eastern Daylight Time. 18 separate 120-second exposures. Robotic telescopes. Remote operation. The comet sits 14 degrees above eastern horizon. 61% moon 70 degrees away. Terrible conditions. But the ion tail shows clear. 0.7 degrees across the sky. Sharp. Luminous. Blue-green glow. Faint anti-tail extends opposite direction. Perspective effect. Dust along the orbit. Massi posts the image. The tail grew dramatically, more structured than September observations. Activity intensifying. Nobody expected this evolution. Most Oort cloud comets brighten gradually. Predictable curves. C 2020, F3, Neowise, C 1995, O1 Hale Bop, 1P Halley, all follow standard patterns, pre-perihelion brightening scales, with heliocentric distance to the -2 or 3 power. 3I Atlas, -7.5. The deviation suggests compositional exoticism, something inherited from formation in an extrasolar planetary system. Different star, different disk chemistry, different volatile inventory. The rapid brightening might connect to carbon dioxide dominance. CO2 sublimates at lower temperatures than water, starts outgassing farther from the sun. Maybe it cooled the nucleus early on, kept water ice frozen longer, held down H2O sublimation rates, then at perihelion temperatures cross a threshold. Buried water layers heat up. Cascade sublimation. Sudden surge in gas production. Dust lofted into space. Brightness spike. The cooling effect from CO2 sublimation at large distances could explain why activity remained modest until close approach. Then the dam breaks. Another possibility. Structural oddities. Nucleus shape. Composition layers. Porosity. Thermal conductivity. Any of those could drive unusual outgassing. The object might have acquired peculiarities during its long interstellar journey. 3 billion years old. Maybe 7 billion. Hopkins and colleagues estimate dynamical age, thick disk galactic population, low metallicity star, heavy element abundance 40% of solar, ancient, twice the age of our solar system, interstellar radiation processing, cosmic ray bombardment. That changes ice structure, creates chemical impurities, physical behaviors distinct from native solar system objects. Davide Farnocchia at NASA Jet Propulsion Laboratory detects non-gravitational acceleration. October observations. The comet's trajectory deviates from pure gravitational motion. Jets of gas and dust act like tiny thrusters. Rocket effect, subtle but measurable, typical for active comets, confirms ongoing outgassing. The acceleration implies mass loss, AV. Loeb proposes fragmentation. Harvard astronomer claims the brightening and jet behavior could mean 3I Atlas broke into pieces, maybe 16 fragments. Fireworks at Perihelion. Other astronomers push back. Jason Wright's group at Penn State. Same data fits a very active but intact comet. No measurements indicate orbit change. The brightening doesn't require disintegration, just intense sublimation from a chemically unusual nucleus. The radio detection adds another layer. Meerkat radio array in South Africa detects hydroxyl absorption lines, OH radicals. Water molecules in the coma break apart under sunlight. 1H2O plus ultraviolet photon produces OH plus atomic. Hydrogen. The hydroxyl footprint confirms natural comet activity, not an alien probe. The team notes this explicitly. Detection confirms the object is a natural comet. For radio astronomers, the OH signature is exactly what they hope to see from a wet interstellar comet near the Sun. Gives another way to track water loss rates. The SphereX observations, August 21, 2025, show water ice and bright carbon dioxide emission. NASA's SphereX mission. California Institute of Technology team. Mid-August data. Carbon dioxide gas glowing. Water ice particles reflecting light. Nickel emission detected same day by VLT. Cyanide. Confirmed. The multi-wavelength coverage builds a complete chemical profile. Infrared from JWST, ultraviolet from Swift Observatory, optical from ground telescopes, radio from Meerkat. Each wavelength reveals different molecules, different processes. Together they map the nucleus composition. Hubble Space Telescope joins July 21, 2025. First images. High detail coma structure. Constrains nucleus diameter. Between 0.32 and 5.6 kilometers. Most likely less than 1 kilometer. Small, compact, dense. The size estimate comes from brightness and how much light the coma scatters. Can't separate nucleus light from coma glow directly, but the numbers bracket its sub-kilometer nucleus with massive atmosphere. Classic comet architecture. November 2025. Hubble performs ultraviolet spectroscopy. Measures gas emission composition, sulfur to oxygen ratio. Ongoing monitoring as the comet recedes. JWST schedules next observations. December 2025. Post-perihelion, after closest solar approach. Catch the object as it heads back to interstellar space. See what changed, what survived. Did the blue color persist or shift again? The December observations will show if activity plateaus or fades, if mass loss continues or drops, if the chemical signature evolves. December 19, 2025. Closest approach to Earth, 1.8 astronomical units, about 270 million kilometers. No danger, safe distance, but prime observing window. Ground-based telescopes, Hubble, JWST, major facilities all planned. Check if the nucleus stayed intact. Look for fragmentation signatures. Measure brightness, spectrum, activity level. If Loeb's fragmentation hypothesis holds, the comet should appear dimmer, dispersed, multiple pieces separating. If it stayed whole, the nucleus keeps outgassing. Single bright source, we'll know in December. If you value documented cosmic visitor analysis like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from the James Webb Space Telescope, NIR spec observations, published by Martin Cordiner on August 25, 2025, in arXiv paper 2508.182. C209, showing the 8:1 carbon dioxide to water ratio, and from the Meerkat radio detection confirming hydroxyl absorption lines documented in multiple astronomy outlets, November 2025. Now back to the information. The color change narrative needs correction. Multiple outlets reported 3i Atlas changed color 3 times. Red, green, blue. Chicheng Zhang pushes back. Lowell Observatory postdoctoral fellow, co-author on the Perihelion brightening study, clarifies the situation, November 2025. The blue-green hues don't indicate color changes. They reflect increasing gas coma visibility as outgassing intensifies. The gas coma showed blue-green since early September, before perihelion, dicarbon molecules, C2, fluorescence under ultraviolet sunlight, characteristic cometary emission, common feature, not anomalous. The confusion stems from mixing observations, dust coma versus gas coma. Early observations showed red dust, mineral particles reflecting sunlight. Later observations emphasized gas emission, blue-green from carbon molecules. Different components, different colors observed at different times, observed with different instruments and filters. Not a transformation, just revealing different aspects of the comet's structure. Zhang states clearly, the blue appearance represents normal cometary chemistry, not mysterious behavior. The gas composition causes the color. Carbon dioxide, cyanide, dicarbon, all emit in blue-green wavelengths when excited by solar radiation. But the perihelion blue shift, that's different. The LASCO and CCOR1 color photometry near perihelion, October late 2025. That shows bluer than sunlight, not just blue-green gas emission against black space, bluer than the solar spectrum itself. That requires gas emission contributing substantial fraction to overall visible brightness. Dust would redden it, cold surface would redden it. Only hot gas emission or extremely efficient fluorescence processes can push the color bluer than the source star. Zhang and Battams document this. The preprint states it explicit. Color photometry shows the comet to be distinctly bluer than the sun, contrast to earlier observations showing comet's dust to be red. So what causes the blue shift at perihelion? Gas emission from C2 and possibly NH2 contributing sizable fraction to overall visible brightness. As the comet heats up approaching the sun, volatile sublimation accelerates. More gas, more molecules, more fluorescence. The gas glow overwhelms dust reflection near perihelion, changes the integrated color, makes the whole object appear bluer. Standard physics, just unusually intense because of the chemical composition. That carbon dioxide dominance, that extreme CO2 to water ratio, drives high gas production rates, produces a brilliant glowing atmosphere rich in carbon species. The 3 color change narrative collapses under scrutiny. July discovery, faint, dust dominated, slightly red, normal. September observations, activity increases, green from cyanide and dicarbon, normal. October perihelion, behind the sun, solar observatories see blue, gas emission overwhelms dust, still normal, just misreported, as transformation. Scientists clarify. Media sensationalism creates false narrative. The comet behaves like a comet, outgassing near the sun, forming a coma, developing a tail, following expected patterns. The chemistry is exotic, the brightening rate extreme, the nickel without iron puzzling. But the color changes. Misinterpretation of different observations showing different coma components at different activity levels. One legitimate mystery remains. Why blue near perihelion specifically? The carbon dioxide dominance explains high gas production. But why does the emission overwhelm dust reflection so completely at closest approach? Most comets maintain visible dust tails, even near perihelion. 3i Atlas shows gas dominance. The JWST data provides clues. Low dust to gas ratio. CO2 outgassing produces less dust than water sublimation. Carbon dioxide ice sublimates cleanly. Doesn't lift as much particulate matter. Water ice drags dust grains, creates thick, dusty coma. If 3i Atlas nucleus is genuinely carbon dioxide rich with low water content, the dust production stays modest. Gas emission dominates the optical signature, explains the blue appearance. The anti-tail adds visual complexity. November observations show faint anti-tail extending opposite the main ion tail, not physically pointing toward the Sun. Perspective effect. Earth passes through the comet's orbital plane. Dust particles left behind along the orbit form a sheet. From our viewing angle, the sheet appears as a spike pointing back. Optical illusion, but real dust. Legacy of earlier outgassing events. The dust trail traces the comet's path through the solar system, maps where it's been, shows the material it's shedding. The Virtual Telescope project tracks evolution. November 6th image, then November 10th. Tail grows longer, more structured, better defined. Activity increasing as post-perihelion heating reaches deeper nucleus layers. Even moving away from the Sun, the sublimation continues. Thermal wave penetrates inward. Buried ices heat. Up. Delayed outgassing. Common in comets. The surface heats first on approach. Interior stays cold. After perihelion, the heat wave progresses inward, triggers deeper ice layers, sustains activity past closest approach. 3I Atlas follows this pattern. November observations show maintained or increased tail development despite receding from perihelion. Brightness predictions vary. Some models suggest magnitude 11 to 12 under normal conditions. Optimistic forecasts hint at magnitude 9 if heightened activity continues. Either way, brighter than most interstellar objects. Oumuamua never showed a coma. Too faint. Too fast. Gone before detailed spectroscopy. Borisov showed coma. Water dominated. Familiar chemistry. Magnitude 15 at discovery. Faded quickly. 3I Atlas? Discovered at magnitude 17 in July. Rose to magnitude 7 or 8 near perihelion. Emerging into November morning sky around magnitude 10 or 11. Small telescopes can detect it. Astrophotographers capture it. Citizen science networks like Unistellar monitor it. Global community tracking an ancient visitor from another star. The discovery itself came fast. July 1st, 2025. Atlas survey in Chile. Asteroid terrestrial impact, last alert system. Designed to find near-Earth asteroids, catches a comet instead. Designation C, 2025 N1, Atlas. Third interstellar object. 3I. The orbit calculation reveals hyperbolic trajectory. Eccentricity over 1. Velocity exceeds escape speed. Coming from interstellar space, heading back to interstellar space. One-way trip. 53 million years to reach us from its origin system, maybe more. Drifting through the void. Then sunlight touches it, wakes it up, starts the outgassing, gives us 6 months to study it before it fades forever. Pre-discovery images exist. Backtracked to mid-June 2025. Faint dot on archived survey plates. Confirms the trajectory, refines the orbit, shows it came from the general direction of the galactic thick disk. Old population, metal-poor stars, ancient systems. The velocity relative to the local standard of rest hints at long journey, not recently ejected. Been wandering for billions of years, saw the rise and fall of stellar generations, witnessed supernovae, passed through molecular clouds, survived radiation, temperature cycling, impacts from interstellar dust grains. Each epoch left marks, altered surface chemistry, modified ice structure, created the weird ratios we measure now. The parent star remains unknown, could be dead. White dwarf, neutron star. The comet might outlive its origin system. Planetary system disrupted. Star evolved off main sequence. Planet scattered or consumed. Only the ejected comet survives, carries the chemical fingerprint of a vanished world. The carbon dioxide dominance, the nickel emission without iron, the extreme isotope ratios, all clues to conditions in a protoplanetary disk we'll never see. Around a star we can't identify, in a system that might not exist anymore. Formation scenarios get speculative. Beyond the CO2 ice line implies great distance from parent star. Cold region of the disk, low stellar flux, but carbon dioxide needs carbon and oxygen. The disk must have contained both. Carbon to oxygen ratio matters. Solar metallicity environments produce certain ice mixtures. Different ratios shift the chemistry. If the parent star had higher carbon to oxygen than solar, the disk favored carbon-rich ices. Carbon monoxide, carbon dioxide, organic compounds, less water. That matches 3I Atlas composition. Radiation processing offers alternative path, form as normal comet, water ice, silicates, organics, get ejected into interstellar space, spend billions of years absorbing cosmic rays, ultraviolet photons from distant stars, galactic background radiation. The bombardment breaks chemical bonds, drives photochemistry. Water ice sublimates or gets converted to other compounds. Volatiles lost to space. Carbon dioxide resists radiation damage better, stays frozen longer. Surface layers get stripped. Deeper layers enriched in radiation-resistant species. By the time it reaches our solar system, the original composition is gone, replaced by processed material. Explains the weird chemistry. Explains the nickel release mechanism. Organometallic compounds form during radiation processing. Explains everything. Testing the scenarios requires comparison. Oumuamua gave no spectroscopy. Tumbling rock, maybe comet core. Dried out, no coma. Useless for chemistry. Borisov showed normal comet behavior. Water dominated, cyanide, dust, familiar ratios. Solar system analog. Proves some interstellar comets match our own. 3. I-Atlas proves others don't. Shows diversity exists. Different formation environments, different evolutionary paths, different end states. Sample size 3, not enough for statistics, but enough to show variety. Future detection rates matter. Vera Rubin Observatory starts legacy survey of space and time. LSST, deep, wide field, nightly cadence. Should detect many more interstellar objects, maybe tens per year. Build population statistics, measure composition distribution, test formation models. 3I Atlas becomes first of many. Template for comparison. Reference point. Its weird chemistry might prove common or unique. We need more data. The Juno mission redirection proposal went nowhere. NASA spacecraft orbiting Jupiter. Primary mission ending. Could execute trajectory change, gravity assist, velocity boost. Intercept 3I Atlas March 2026. Close flyby. Detailed measurements. Near-infrared spectrometer, magnetometer, microwave radiometer, direct sampling instruments. Better data than telescopes. Mission planners resisted. Contamination by artificial intelligence speculation. Stigma from Loeb's alien techno-signature claims. Science opportunity lost. Juno stays at Jupiter. 3I Atlas recedes unsampled. ESA's JUICE spacecraft might catch glimpses. Europa-Jupiter system mission en route. November 2025 could provide distant observations, supplements ground-based data, but no close flyby, no direct sampling, another missed chance. The observation window closes. December gives last good look. Then the comet dims. Distance increases. Surface area drops below detection limits. Gone by early 2026. Back to the void. The physical state after perihelion remains uncertain. Did it survive intact? Did it fragment? Loeb argues for breakup. Brightness and jet patterns suggest multiple pieces. 16 fragments, fireworks. Other scientists see single nucleus, high activity, complex jet structure. No fragmentation required. Observations favor intact nucleus. No secondary brightening events. No dispersed morphology. But definitive answer requires December data. Hubble images. JWST spectra. Ground-based photometry. If fragments exist, they'll separate, show up as distinct sources. If intact, the nucleus appears as single-point source with symmetric coma. Mass loss calculations from Zhang and colleagues suggest significant material shed near perihelion, about 10% of total mass. Massive outgassing, large plume. Should be detectable in November-December observations. Extended coma, thick atmosphere, continued activity. JUICE might spot it early November. European Space Agency monitoring, but preprint predictions uncertain, model dependent, need real data. Post-perihelion fading unclear. Plateau possible. Brief continuation of brightening possible. Rapid fade possible. The CO2 dominance complicates predictions. Carbon dioxide activity extends farther from Sun than water-driven outgassing. 3I Atlas might maintain brightness longer than typical comets, or the low water content means less sustained activity. Surface heats fast, interior stays cold, activity drops quickly, can't predict without precedent. 3I Atlas is unique, no comparison objects, wait and watch. The ion tail evolution continues. November images show growth, structure, complexity, plasma dynamics, solar-wind interaction, magnetic field draping. The charged particles stream away at hundreds of kilometers per second. Tail stretches millions of kilometers. Points directly away from Sun regardless of comet motion. Disconnection events possible. Magnetic field reversals in solar wind. Sever the tail. Comet grows new one. Dynamic process. Changes hourly. The Virtual Telescope project plans continued monitoring. Regular imaging cadence. Track morphology changes. Build time series. Movie of tail evolution. Spectroscopy reveals velocity structure. Doppler shifts in emission lines. Gas flowing outward. Expansion speed. Typically 1 kilometer per second from nucleus. Faster in jets. Slower in diffuse coma. The velocity field maps outgassing pattern. Identifies active regions on nucleus surface. Sunward hemisphere usually most active. Solar heating greatest there, but rotation affects it. Nucleus spin distributes heat, creates dawn-dusk asymmetries. Complex three-dimensional structure. Amateur astronomers contribute. Unistellar network. Citizen science telescopes, small apertures, 3 to 4.5 inches. Image stacking compensates for faintness. Comet motion tracked. Frames aligned. Co-added. Recovers signal. Measures brightness. Feeds data to professional teams. Democratic science. Distributed observations. Global coverage. Professionals get 24-hour monitoring. Fill gaps. Catch outbursts. Document evolution. Community effort tracking ancient visitor. The isotope ratios probe origin. Carbon-12 versus carbon-13. Oxygen-16 versus oxygen-17 and 18. Deuterium to hydrogen. Each ratio constrains formation temperature. Disk chemistry. Parent star metallicity. The carbon isotopes look solar, familiar, but limited precision. JWST couldn't measure deuterium in water, signal too weak. Dust obscuration need better observations post-perihelion maybe. Stronger activity. Clearer spectrum. Precise isotope ratios distinguish formation scenarios. Test radiation processing hypothesis. Compare to solar system comet data. Build coherent picture. The nucleus rotation period unknown. Light curve variations would reveal spin. But brightness dominated by coma. Can't separate nucleus signal. Rotation affects outgassing pattern. Creates jets. Non-gravitational forces. Torques from asymmetric sublimation. Changes spin rate. Complicates orbit prediction. Need resolved imaging. Hubble resolution insufficient. Nucleus too small. Coma too bright. JWST might resolve it in infrared, where coma emission weaker, but difficult observation. Requires perfect timing. Lucky geometry. Surface composition mysteries persist. Water ice detected by SphereX. But how much? What fraction? Distribution, patches, layers, mantle. The carbon dioxide dominance in gas phase might not reflect bulk composition. Surface layers might be CO2-rich, interior water-rich, or vice versa. Sublimation rates differ. CO2 activates at lower temperatures, sublimates farther from Sun, creates biased sampling. Gas composition doesn't equal nucleus composition. Need direct surface observations. Impossible with current data. Requires flyby mission. Lander. Sample return. Never happening for 3I Atlas. The dust properties remain constrained. Particle size distribution. Composition. Crystallinity. Organics. Silicates. The red color in early observations suggests iron-bearing minerals. Oxidized compounds. But weak dust emission overall. Low dust to gas ratio. Carbon dioxide sublimates cleanly. Doesn't entrain particles efficiently. Dust production concentrated at perihelion. Peak heating. Maximum activity. November should show continued dust tail. Sunlight pressure pushes particles, creates curved trail. Different trajectory than gas. Maps radiation pressure effects. The thermal model predictions varied. Pre-perihelion estimates suggested certain brightness levels, outgassing rates, coma size. Reality exceeded predictions. Brightening faster than models. Activity higher than anticipated. Carbon dioxide dominance not fully accounted for. Models assumed water-driven activity. Solar system template. 3I Atlas broke template. Required model updates. Post-perihelion. Predictions now uncertain. Need new models. Incorporate CO2 thermodynamics. Match observations. Predict future behavior. Science iteration. Theory meets data. Theory adjusts. The non-gravitational acceleration complicates trajectory prediction. Jets push the nucleus, change velocity, alter orbit. Small effect but measurable. Accumulates over months. By December 2025, position uncertainty grows. Effects pointing for Hubble and JWST. Requires updated ephemerides. Regular astrometry. Position measurements. Refine orbit solution. Predict location. Track object. Without good orbit, telescopes point wrong direction. Miss target. Observation fails. Critical for December studies. The legacy of 3I Atlas extends beyond 6 months. Established interstellar. Comet chemistry varies. Proved compositional diversity. Demonstrated detection methods for perihelion passage. Validated multi-wavelength approach. Combined space and ground observations. Involved citizen scientists. Tested fragmentation hypotheses. Advanced cometary science. Raised questions. What causes nickel without iron? How does carbon dioxide dominance arise? Why rapid brightening? What drives blue color at perihelion? Each question spawns research, papers, models, debates, future proposals, next-generation instruments, improved detection methods. The December data drop anticipated. Hubble ultraviolet spectroscopy results, JWST infrared spectra, ground-based photometry compilations, radio observations, X-ray monitoring from SWIFT, multi-wavelength synthesis, comprehensive chemical inventory, updated nucleus properties, post-perihelion activity assessment, fragmentation verdict, mass loss estimates, rotation constraints, all coming, community prepares, manuscripts drafted, analysis pipelines ready, data release triggers cascade, results published, science advanced, then the comet fades. January 2026. Too faint for most telescopes. February. Below detection limits. Gone. Heading back to interstellar space. Outbound trajectory. Hyperbolic. Never returns. Drifts through galactic disk. Next encounter in millions of years. Different star system. Different observers. Maybe no observers. Just silent passage. Ancient ice ball carrying secrets from a dead world. We had 6 months. July to December 2025. Caught it. Studied it. Learned from it. Now it leaves. What remains? Data, spectra, images, measurements, publications, models, debates, memory, the blue shift at perihelion, the nickel emission, the carbon dioxide dominance, the rapid brightening, all documented, all archived, ready for future comparison. When next interstellar comet arrives, when Vera Rubin finds dozens more, 3I Atlas serves as template, benchmark, first of the chemically exotic visitors, proved they exist, showed what to expect, what to measure, how to interpret. Science builds on precedent. 3I Atlas established precedent, and one thing stands certain amid the mysteries. Between September and late October, 2025, as 3I Atlas approached perihelion, the comet transformed from red dust glow to blue gas shine. LASCO coronagraph and CCR1 instrument color photometry measured it. Zhang and Batams documented it. The object appeared distinctly bluer than the sun itself. Gas emission from carbon molecules overwhelmed dust reflection, created an appearance never before recorded in a comet at that intensity. The blue perihelion shine of 3I Atlas. Not alien technology, not mysterious transformation, Just extreme chemistry from another star system heated by our sun for the first and only time. A visitor showing its true nature under solar radiation, then departing forever into the dark between the stars, carrying that blue glow into memory and data archives, where it will outlast the comet itself.